So I'll be talking a little bit about some of the research I've been doing since I joined the lab, mostly on electrochemical nitrate reduction to ammonia using titanium nitrogen-doped carbon nanoflowers. We also call them titanium single-atom catalysts, but we changed the convention of how we name them because a lot of the single-atom catalysts you have out there are really not single-atom catalysts. So we're trying to use a more inclusive wording on that. Um, see how I can. Yeah, so kind of a motivation of the research that I'm doing. It's to close the nitrogen loop and close the kind of the way we talk about and we deal with nitrogen in our systems. So nitrogen is, a very essential molecule for us. We use it to produce fertilizers, and most of the way that we produce fertilizers right now is through the Haber-Bosch process. We take nitrogen from the air and we convert it to ammonia using steam methane reforming, and we use thermochemical processes for that. We produce about 120 teragrams of nitrogen per year. And that process itself emits about 1.4% of our global CO2 emissions. This process, has been great in the way that has allowed us to produce food at the levels that we need as a society to grow. But the caveat with it, consumes a lot of energy and it emits a lot of CO2. Then in the nitrogen cycle, what we have is after we put that ammonia into our fields to make food, we use that food for human consumption, and then some of the waste that comes from humans goes into wastewaters. But a lot of the ammonia and fertilizers that we put in fields actually just doesn't get absorbed by plants, and then that goes into the wastewaters as well. Generally, we use municipal wastewater to kind of like get rid of that ammonia and nitrates in wastewaters, and we convert that to nitrogen. We emit it back to the atmosphere. But those like wastewater processes, they consume about 3% of electricity consumption as well. And we're like turned that into nitrogen. We're going from fixed nitrogen to just gaseous nitrogen. So it's not the most ideal in the way of like utilization because those fixed nitrogen species are very valuable, and then we're just kind of like wasting all that into and turning it back into the atmosphere. And then the final problem we have with the current way we approach the nitrogen cycle is that a lot of those untreated species of fixed nitrogen goes into surface waters. So they end up, that nitrate and ammonia ends up in rivers and lakes, and it causes this thing called algal blooms. So it can create dead zones, and it can affect a lot of the marine life in those lakes and rivers. So it is estimated that in the US, these algal blooms have around 2.2 billion, cost 2.2 billion in damage yearly. So the way that we are addressing this problem is we're doing wastewater refining. So we take the wastewaters that come from agriculture or from human activities, and we create reactive separation devices that allow us to concentrate those wastewaters, convert them to ammonia, and then purify that ammonia and use that as fertilizers. And it is estimated that about 30 to 60% of our current fixed nitrogen supply can be recycled through these methods. And a very central piece of technology that we need to develop in order to be able to create these reactive separation systems is electrochemical nitrate reduction to ammonia. So it is important to create catalysts and systems that allow us to have make this reaction more efficient and scale it up to the levels that we can implement it in industry. So a main challenge with wastewater refining is that wastewaters are generally complex. So there's a wide variety of ions, a wide variety of contaminants, and they also come in a wide variety of concentrations. So it is hard to design a system that will work for all of the wastewaters that we have available for us. But it is important to us to design systems that are flexible enough to kind of like handle wastewaters with different ions and different contaminants. And something that you'll notice is that fertilizer runoff and municipal wastewaters, they kind of make up for most of the global flow rate of nitrogen, and they're generally very dilute. So we have to create systems that can handle, like concentrations in the millimolar ranges to be able to concentrate that and then convert that to ammonia. So that's where it comes to the fact that there's a need to develop these systems that concentrate nitrates initially, then convert those nitrates to ammonia, and then purify that ammonia as fuel. So that's kind of the overarching theme of the research that I'm doing here at Stanford. And today I'll mostly be talking about the conversion part of this research. So we are comparing catalyst activity and selectivity. We're mostly looking at single atom catalyst versus bulk catalysts. Today, I'll mostly be talking about titanium single atom catalysts. And we have created specific catalysts and we're able to control the morphology and the structure of these catalysts. So, for example, we started with carbon nanoflowers, and then we add titanium dope onto these carbon nanoflowers, and we can create titanium dope carbon nanoflowers with very similar structure. And we can also create titanium dope carbon spheres. And we're studying the differences between the activity and selectivity for this specific reaction by changing morphology and titanium doping. The way that we're creating these catalysts is, we're mixing Ti4 plus reagents with inacetone and, with other reagents for this reaction. Initially, we do free radical polymerization, then we stabilize the polymer, and then we carbonize the polymer. And what we hypothesize is that what we end up with is a titanium that is ligated to 4 nitrogens in a carbon matrix. And we spend a lot of time trying to prove that this is the structure that we have. And I'll talk more about later. But the benefits of this is that titanium creates single sites where we can have a very controlled reaction. So they have a very unique structure and activity to this specific reaction. And then the carbon nanoflower architecture creates, a very high surface area nanoparticle that we can use for this reaction as well. So the 2 questions that we have here is what is the catalyst structure and morphology, and how do these catalysts compare to bulk titanium? So the first thing that we did is, we wanted to make nanoflowers, and what we found is the more titanium that we have, so the more titanium loading that we add initially in this synthesis procedure, it affects the way our particles agglomerate. So you can see that most of them have a petal-like structure, even at very high titanium loadings. But once you kind of pass that 0.1%, 0.1 weight percent of titanium, you can see that the particles start to agglomerate. So we, didn't really want that in order to kind of maintain that nanoflower architecture. So for most of the research I'll be presenting today, I'll be showing you this 0.1%, 0.1 weight percent nanoparticle. And it just happens to also be the best one in terms of performance. So that's why we went with it. The second question that we had is, do we really have a single atom catalyst, or do we have a cluster of titaniums? So what can happen when you're synthesizing this is you might be calling it a single atom catalyst, but you might have the formation of nanoparticles in the surface of the catalyst, which that's no longer single atom. And you might be able to achieve this denser single atom catalyst if you have good synthesis procedures. But there's, that's a whole other avenue of research. So in order to answer this question, if we really have this structure, we use XRD to probe the crystallinity of our catalyst, and then we use XAS and XPS to probe the composition and chemical states in which we have. And we can confidently say at the end of this, we know what the structure is. So I won't spoil it until I say it. But first, we did XRD. So on the left, you can see the XRD for the carbon nanoflower without any titanium doping. And then the 0.1% titanium on carbon nanoflower that has titanium doping, but you can see that there's no titanium peaks, showing that there's no to very little crystallinity on the titanium that is in the nanoflower. And if you increase the titanium loading to 0.7, you can see that you start seeing some peaks for anatase and rutile and some other crystalline titanium forms, which indicates that there's titanium nanoparticles forming and agglomerating in the surface of these nanoparticles. Then we did NKH-XAS, which provides direct evidence of 3 nitrogen moieties. You can see that in the red line over here, that's your carbon nanoflower without any titanium doping. And then the black and blue lines are titanium carbon nanoflower and titanium carbon sphere. You can see that the pyridinic and the graphitic peaks for nitrogen are present in all of these curves, but the pyrolytic peak of nitrogen is only present in the titanium doped species. So that indicates that this is kind of sending us in the direction that we think that the titanium is ligating atomically to these pyrolytic nitrogen sites. And then since the other thing that we know here is we know that the structure, we're expecting those 3 peaks. So then when we do N1S XPS, we can deconvolute it into 3 peaks based on the XAS data. So we deconvolute it into the graphitic, into the pyridinic and the pyrolytic curves. And then from the XPS, we can estimate the atomic content of this pyrolytic nitrogen, and we estimate it to be around 0.71 atomic percent. And because we know that the structure has 4 nitrogens per each single titanium that we have, we estimate that the titanium content for these nanoparticles is about 0.18 atomic percent. And this, also supports the hypothesis that we have that the titanium is ligated to this pyrolytic nitrogen. Then we did OKH for O1S XPS. So we did as well XAS with XPS bound to it. We see in TiO2 rutile, you can see the TiO bonds here. And then in our nanoparticles, we see our carbon oxygen bonds and our hydroxide bonds, which are generally always there in these carbon supports. But we see a kind of slight appearance of these TiO bonds over here, which it indicates that we do have some titanium being bonded to oxygen as well, besides nitrogen. And when we do XPS on this oxygen, we can see we fit the TiO bonds, and we can also estimate how much of this titanium we have, which I think both of the titanium combined ends up being to about 0.5 to 0.6 atomic percent in the nanoparticles. We hypothesized that these TiO bonds aren't really in the single atom architecture. They come from the surface oxide of titanium nanoparticles that are somewhat forming in our nanoparticles. So we have some titanium being clustered when we make these catalysts. That's why we don't really call this catalyst titanium single atom catalyst, and we tend to call it titanium doped carbon nanoflowers because it is in some way a matrix of both single atom sites with nanoparticles dispersed in the catalyst. And then finally, we do Zanes to study the titanium oxidation state. So we do Zanes and we study the edge absorption energy for all of these different standards. So you have titanium, which has an oxidation state of 0. You have TiO2, which has an oxidation state of 4. And then you have these ones kind of in the middle with oxidation states of 2 or 3. And we study this edge absorption energy. And we can plot the absorption edge energy versus the oxidation state to kind of get an idea of where our catalyst would be. And based on this, we estimate that our catalyst has oxidation state of about 3.6. This is mostly follows kind of the idea that we have for the structure of the catalyst being ligated to 4 nitrogens. It is not perfectly 4 because the number can be brought down if you have some nanoparticles that are in the titanium state that have an oxidation state of 0, but it is close enough with 4 that it kind of is consistent as well with our use of Ti4 as a precursor. Now that we have fully characterized our catalyst, we will do the electrochemical characterization of it because we want to essentially figure out what are the best electrolytes and in which conditions does this catalyst performs the best. To do this, we first grind our catalyst with mustard and pestle because it agglomerates into bigger chunks and we want to make it into a fine powder. We disperse it in IPA, we mix it with Nafion, and then we spray coat it into carbon paper. And we put it in this sort of H cell in which we have an electrolyte compartment on the cathode, on the anode, an electrolyte compartment on the cathode, and then we scorch both sides with argon gas, and whatever comes out of this chamber goes into an acid trap and then goes into our gas chromatograph. So from the electrolyte chamber, we're able to quantify nitrates, nitrites, hydroxylamine, and we also quantified ammonia. In the acid trap, we quantified whatever ammonia volatilizes, and then in the gas chromatograph, we quantify hydrogen and nitrogen if we make any, which we don't make any nitrogen. So we end up just quantifying hydrogen. The first thing that we wanted to figure out was the pH range that we should be operating this system at. So we deposited this catalyst on a carbon rotating ring to be able to get rid of all mass transport limitations and just study at the activity of this catalyst. So we studied this catalyst in pH 1, pH 7, and pH 14. What we see is that this catalyst is significantly more active in very alkaline electrolytes compared to very acidic electrolytes, which this was actually a sort of a surprise to us because I don't know if anyone has used titanium foil for nitrate reduction to ammonia. It only really works well in very acidic environments. So it is the same, the same material, but it's in a different configuration. And we hypothesized that it's because titanium for doing this reaction needs a lot of availability of protons per active site. And because we're minimizing the amount of active sites of titanium here, we can kind of like, we have different needs of proton availability and we can operate at very high pH compared to titanium foil. And then we add different counter ions, we add perchlorates, we add sulfates, and we try to kind of improve the base performance compared to just NaOH at pH 14. What we see is that sulfates generally leads to the best performance, and perchlorates, I think the issue with perchlorates here is that it usually has worked well for us when we just have like bulk titanium or metal electrodes, but because we have a carbon electrode, the perchlorate, I think it ends up corroding that electrode, and then some of the electrons actually go to that decomposition and corrosion of the carbon electrode, and that's why you see that the bar doesn't really add up to 50%. We think that some of those electrons are going to the degradation of our catalyst. But with sulfates, we can close that mass balance to over 90%, and we get pretty good performance for nitrate reduction to ammonia. Now that we have selected our catalyst, we do a bigger survey in which we are trying to survey the different potentials and study the product distribution, and to give us an idea of the mechanisms and how we can improve this reaction further. So at very less negative potentials, so at 0.55, you can see that nitrite is the dominant species. Once you go around 0.7, the nitrite gets suppressed and you have a lot of ammonia as your predominant species. And after 0.7, so at 0.85 and 0.1, hydrogen starts becoming more active and you start seeing hydrogen as your predominant source of ardite efficiency. So the kind of optimal performance for us to operate is negative 0.7 versus RHE. And any higher than that, you have a lot of competition versus hydrogen, and anything lower than that, nitrite is the predominant species. And then we kind of study at how the partial current densities compare to this. And what we see, which makes us hypothesize that we are having some mass transport issues because our cell doesn't really have any flow, it's just stagnant in the electrolyte chambers. You see that once you start going past 0.85, your ammonia current density plateaus, but your hydroxylamine and your nitrites increase slightly throughout the whole potential range. And we think that we hypothesize that some of those nitrites and hydroxylamines that are normally intermediates to ammonia, they end up getting desorbed from the catalyst surface and they don't get reabsorbed because they dilute into the electrolyte, and we have this thick kind of almost like 1-inch chambers or half an inch chambers that don't have any flow. So we think that we can improve this one now that we're moving to flow type reactor architectures. So having serpentine and flow management channels should allow us to have better mass transport there. And then we look also as well to where our nitrogen species are going. So we start with nitrate, and we have different kind of pathways we can follow on different products. And we want to make sure we're accounting for our mass balance, and we're accounting where all of our nitrogen is going. So it is pretty similar in the way that, you at very low potentials, you have nitrite being the predominant species, and at very high potentials, there's kind of a mix between nitrite and ammonia. And then it is important to know that hydroxylamine kind of like remains almost in the same order of magnitude across the full experimental range. But we see something pretty similar as well with where our nitrogen is going. You can see that, even though a lot of it goes to ammonia, that contribution plateaus after 0.85, and the nitrite grows as well as the hydroxylamine. So this further corroborates our hypothesis that we're having some mass transport limitations, and we're addressing that right now by moving to electrolyzer that has flow channels and flow architecture. And then finally, for the impact of the morphology and the titanium doping, we compare titanium doped carbon nanoflowers with titanium doped carbon spheres and just pure carbon nanoflowers. What we see is that we are able to double the ammonia production current density. So we're doubling the yield and the rates at which we're producing ammonia, compared to both the titanium doped carbon spheres and the titanium and the undoped carbon nanoflowers. So this indicates the importance of having both a titanium doping and titanium sites, but also the kind of improvements that we can get from having the enhanced surface area that the carbon nanoflowers provide. And we compare the performance of these different nanoparticles, and you can see that the selectivity of the titanium doped carbon nanoflowers improves by amounts. It doubles compared to the nanospheres and the carbon nanoflowers, as well as the nitrogen balance almost nearly more than doubles. And you can see that both the carbon nanoflowers, and the titanium doped carbon spheres lead to a lot more ammonia, a lot more hydrogen production compared to ammonia, and also they produce a lot more nitrates and hydroxylamine. So we have kind of optimized this catalyst to be more selective towards ammonia. And yeah, in summary, we can understand the chemical structure of our catalyst using the advanced characterization facilities that we have here at Stanford. We partner with SLAG, which is our closest closest lab that we can go to do all these XAS and XPS and XRD experiments. We have shown that the titanium doping in the carbon nanoflowers can improve the ammonia production rate by over two times compared to the doped carbon spheres and the undoped carbon nanoflowers. We identified that the optimal voltage is about -0.7 versus RHE, which it is not very ideal because there's some better catalysts out there. Right now, I'm working with cobalt and copper, and those are generally, you can operate those at 0. So you have a 0.7 volt over potential there. That is not very good once you start doing technoeconomics. And we kind of can identify the different regimes. So at lower voltages, nitrate is more of the predominant product, and at higher voltages, hydrogen becomes more predominant. And finally, we started this project to see if we could make a catalyst that would work well in an alkaline environment that was titanium based. This was contradictory to what we usually see in titanium foil, which is usually alkaline, but we get it's usually in very acidic conditions, but we get a couple benefits from operating in alkaline environments because any ammonia that we produce is going to be, in the gaseous state. So it's then very easy to concentrate and purify because you can just have an acid trap that kind of captures that ammonia into ammonium. If you were to operate in an acidic electrolyte, then it's a lot harder to separate your ammonia from that electrolyte because it's going to be in the ammonium ionic phase, and then it's a lot harder to kind of like separate it and purify it. So that's why we want to operate these systems in the alkaline environment. Um, and to kind of like acknowledge some people in my lab. So, really grateful to Dr. Tarpeh, who is my advisor now. And also I worked with Matthew at the start of this project. He was actually here for about a week before he left. So I had to do a very quick turnaround and training when I started my postdoc here. But it's been a really good experience so far. He's now a postdoc at MIT. And yeah, this project has been funded mostly by DARPA. And these are all the lab members from the Tarpeh Lab. We have a pretty big lab and it's a pretty friendly lab. So if you have any questions or want to know more about the lab, you can reach out to my email down there as well. But yeah, thank you so much for letting me give this talk. And if you have any questions, feel free to ask.